to get systematic agreement with the experimental value, where you can actually improve the result by increasing the basis set and maybe improving the accuracy of the calculation, you need to go to the wave function based method. And one of the common options in ORCA to do accurate wave function based calculation is to use the equation of motion approach, and many people gets confused by the fact that what is an equation of motion. So, in the equation of motion approach, the ground state Schrodinger equation is solved like this, and the target state Schrodinger equation is for the kth target state. This is the Schrodinger equation. Now, when I say kth target state, it may be an ionized state, electronegative state, or an excited state, can be a double ionized state, double electronegative state, triple electronegative state, triple ionized state, like that. So, it can be any target state. In the equation of motion approximation, the target state wave function is related to the reference state wave function by a linear operator R k, and with the little bit of mathematical manipulation, you can show this equation as a commutator with respect to the Hamiltonian, and by using this equation you can calculate the energy difference between E k minus E 0, which is omega k. Now, for the if your target state is excited state, then you will get excitation energy. If its target state is an ionized state, you will get ionization energy. If your target state is an electron attached state, you will get the electron attachment energy or the electron affinity. Now, the equation of motion couple cluster method derives its name from the fact. So, this is general equation of motion, and it goes to the works of D.G. Rowe, and its couple cluster variant is actually obtained where your reference state wave function psi 0 is generated by the action of an exponential operator on a Hartree-Fock wave function. This phi 0 is an Hartree-Fock wave function, and in the form of couple cluster, this is actually developed, was in India in ISCS by the group of Professor Devashish Mukherjee. So, if I want to see excited EOM-CCSD, EOM-CCSD like any other couple cluster, singles doubles is the most common approximation. So, in the case of CIS, what we were doing, we were restricting ourselves only to the single excitation space. Whereas, for EOM-CCSD, there is also a double excitation space. So, your excited state not only have contribution from single excitation, but also have contribution from double excitation. That is why they are much more accurate than a CIS. So, you can do the calculation like this. So, everything looks same. In place of TDFT or maybe HF, you just get right EOM-CCSD, and here they are called MDCI. So, it is matrix driven CI, and in the matrix driven CI block you give n roots is equal to 10. Everything else remains same. The things which you can change, EOM-CCSD methods in ORCA currently cannot use the symmetry option. So, I have removed it, and also because I am now doing electron correlation, I also need the auto-aux option to fit the correlation basis, auxiliary correlation basis set. You could have used any other option also for like any other auxiliary basis set also for doing this calculation. Remember, because this scales the both ground and excited state actually scales as n to the power 6 power of the basis set, these are actually quite expensive calculation, and like unlike TDFT, these results converges very slowly with respect to the experiment. So, EOM-CCSD calculation should be only done for very small systems, and if you are interested in super accurate numbers. If not, then it is generally a good idea to stick to TDFT or some cheap methods. ORCA actually has CIS parenthesis D, ADC2, the double hybrid functional can be a very good approximation. It is a slightly higher cost than the normal CIS or TDFT, but less costly than an EOM-CCSD calculation. EOM-CCSD calculation beyond maybe 8 or 9 atoms, unless you use additional approximation, they are not practically feasible in any reasonable basis set. So, now let us make another input file. Let me make it H2CO EOM. Also, I am not keeping the large print because we already know how the molecular orbitals looks like. So, I can submit the UMCC job. And this can take some time. So, our calculation is done. In the equation of motion, there is a different left and right eigenvectors. So, you will get a left and right transition moment, and this will be the final transition moments. So, looks like looks similar to what you will get in a CIS calculation. Even the analyzing the excited state is also very similar. If you see it 7, 10, 7, 8, and percentage singles characteristic tells how much of it is dominated by single excitation. So, let me put the values there. So, from 4.57 in CIS it becomes 4.04, 7.17, 8.19. So, for the Rydberg state, actually sometimes the improvement is high-lying Rydberg state, the improvement can be enormous, and the last one is 8.26. So, these are much better agreement than what you will get in the CIS. Now, for the IP variants, what happens is that you can get a thing where it will generate the singly ionized configuration as well as the so called doubly ionized configuration, which is often called satellite state. Now, remember, this not only can get you to the ground state of the ionized thing, you can get to all the excited state of the ionized state, where the ionization actually happen from inner orbitals also. That is the advantage over the so called delta based calculation, where you do two separate calculation for the neutral and the cation and subtract them to get the IP values. So, for the EA, what happens is that you start with an electron state and add one electron. So, it can add one electron in the LUMO, it can add in the LUMO plus 1. So, you get the ground state of the anion, excited state of the anion, and all the so called satellite state also. And this way of calculating electron affinity is much better than the delta based calculation, because the delta based calculation suffers from what is called a variational collapse of the wave function. So, you can do the IP and EA-EOM-CCSD calculations also in ORCA, and because of the DLPNO approximation, this IP and EA-EOM-CCSD DLPNO calculations you can actually do over pretty large molecules. So, up to 50 to 100 atoms you should be able to do the IP and EA DLPNO calculation. You just need to add DLPNO in between EA-DLPNO CCSD. That will give you not only the ground state of the anion and the excited state of the anion. You should consider the ORCA manual for more details. Now, we talked about only singlet calculation. The excited state can be triplet also, and so these are the triplet excited state looks like. You can see in the superscript I have put a 3. The state ordering is different. So, the first one is A2, the second one instead of B2 it is A1 now, and then comes the 2B2, and these are the corresponding experimental values. So, what I will do is that I will use the Cambridge relief and put triplet is equal to true in the input file. triplet dot INP. और का came H2CO can be 3-leaf triplet So, if you give the triplet option, it will also calculate the singlet with the that of that, and first it will calculate the singlet and then will calculate the triplet. So, in this case of singlet we have seen the S square operator is 0, but in this case you will see the expectation value of the S square operator is 2 and multiplicity is 3. So, the first one is 3.28. Next one is A1. This ordering is also the change in the ordering from singlet to triplet. If you go to the singlet, you will see the second state is B2. In the case of triplet calculation, the second state will be A1 and this is 5.82. For 3 B2 next one will be B2 6.79. And this is 7 point, the other B2 is 7.70. So, the results are slightly underestimated as comparison to the experiment. Although this experimental value actually has a considerable range, if you go to the original experimental paper, you will see that they actually has a considerable range, and if you look at the nature of the transition, you can see the first one is a HOMO to LUMO triplet excitation Rydberg. So, you can do the similar analysis like what we have done before for the singlet excited state. So, up to now what we have discussed is about valence and Rydberg kind of excited states. There is a third kind of excited state which are also quite common, and this is called the so called charge transfer excited state. And charge transfer excited state is the Achilles heel for DFT and even for many of the wave function based methods. Achilles is the hero in the novel of Homer, Iliad, when he was his mother has dipped him into a holy river, so that his body, wherever the holy river water touched, it cannot no weapon can cut him there, but as his mother hold his legs to dip him, so his legs were not had that protection, so they were vulnerable. So, the word Achilles heel is often used to give that to give the impression that this is where something is vulnerable. So, DFT methods are vulnerable to charge transfer transitions, and this is an example of zinc bacteriochlorine, and this example is taken from this Jack's paper. This Jack's paper is by Andreas Drive and Martin Hedgorden, and this is a nice system where two pi rings are connected by a bridge. Now, if you calculate this excited state using B3LIP, I am not talking of chem B3LIP. If you just use a normal B3LIP, you will see that all low lying excited states are actually charge transfer in nature, and you do not see this charge transfer excited state in your experiment. whereas the valence from the experiment, all the excited states are actually, the low lying excited states are actually valence in nature. In the case of B3-lip calculation, TDFT with B3-lip, they are actually comes into the valence excitations actually comes into a much higher energy. So, to say that in the case of B3-lip you will get charge transfer transitions which are not there in experiment, and if you do an EOMCC, the similarity transform version of the EOMCC, these results are not taken from this manuscript. These are my unpublished results, which I have never published, I do not know why. But if you do these STOMCC calculations, you will see that STOMCC is the accurate wave function based method. You will see that all these low lying states are actually valence in nature, and that is what you get in the experiment. So, these charge transfer states are spurious, and this problem of charge transfer, spurious charge transfer state in DFT is so problematic that in many of the paper where people have tried to interpret their experimental results, predicted the lowest lying state is from charge transfer, which is actually an artifact of the DFT method. So, the real experiments, the actual nature of the state is quite different. So, one need to be very careful while using DFT calculation for excited state because of the problem of charge transfer. Now, the CHEM-B3-lip method, the CHEM-B3-lip functional, because it is a long range correction, it has a long range correction. So, they generally does not give these spurious charge transfer states. For the charge transfer state, they are going to give quite accurate results. So, now we are going to go to an example where we will see a charge transfer state, where we will see an actual charge transfer state, not spurious charge transfer state. And if you have free time and have some free computation facilities somewhere, you can draw the structure maybe for a fun and optimize it and do the calculation and see, at least do the B3-lip and CHEM-B3-lip calculation and try to see the difference if you like.